All right, so what we're looking at today is what we call related rates. All right, now when you hear rates, you should think derivatives, okay? But here's the thing. We're going to have multiple derivatives within the same problem. And, or I should say, derivatives of multiple variables within the same problem. And this is just like what we did on this last problem we were looking at in homework, where you took the derivative of a relation that had x and y in it, but you took the derivative with respect to t, and you were acting as though the both x and y were functions of t in that case. So the situation that we're dealing with here is we're going to be dealing with a variety of formulas, okay? Those of you prepping for SAT who have been studying your geometry formulas, you've got a good head start. If you forget some of those, you're going to have to review a little bit. But basically the idea is this. You know, we have some kind of a situation like the one we have here. We have water that's getting drained out of a conical tank. A conical just means cone-shaped. All right? A cone-shaped tank. The volume V, the radius R, and the height H of the water level are all functions of time. If we really looked at them all, we could look at V as a function of time. We could look at the height as a function of time, or the radius as a function of time. All right?
How is height related to time?
Well, the height or depth, you could say, of the water, you could see here as the puddle gets bigger underneath it, okay? The water is draining out of this cone. The height is going to get smaller. The radius is also going to get smaller as time progresses, okay? And of course also here, the volume of water that's left in the cone is going to get smaller over time as well. Okay? But here's the key. When we're looking at a situation like this, the thing that we need to do is we need to make sure that we try to find a formula that relates all of the variables together. And in this case, our volume formula for a cone, volume equals pi r squared h over 3, gives us that relationship. Okay? That's why this is called related rates. We're going to be doing derivatives on formulas that show a relationship between multiple variables.
And how would we find that formula? Just like memorize it?
Yeah, that's one that you ought to know. Okay? The volume of a cylinder. Remember, the volume of a cylinder. Is pi r squared h, and the volume of a cone is pi r squared h divided by 3. Okay? So we're dealing with the cone here, so that's the formula that we're going to use. So we want to take the derivative with respect to time of this formula. So we're taking the derivative with respect to time of v, and we're taking the derivative with respect to time of the pi over 3 r squared h. Okay? So, how would we write the derivative with respect to time of v?
Just like that.
V.
Yeah.
Just dv over t.
Or dv dt, right?
Oh, yeah.
dv dt. Okay? Then we have this other part. This one's a little more challenging. The pi over 3 I'm just going to pull out in front because it's multiplied. So now I've got to do r squared h.
I know how to do it. 2rh plus...
What are you using? Help us out here.
Product rule.
Product rule, okay,
Product
so...
rule. And chain rule.
So 2r...
Oh no, never mind, no chain rule.
dr dt.
dr dt. We are using the chain rule. Because we're taking the derivative of something that's not the independent variable, okay? So it's 2r dr dt
H.
Times dh dt.
times h.
Oh, times h.
That's our f prime g in the formula, right? F prime g plus f g prime. So plus
R squared
DHDT.
dH/dt.
Can you go? Yay!
Okay, so remember here with our product rule. There's the F, there's the G, if you will. Okay, so the derivative of r squared is going to be 2r dr dt.
Yes.
Implicitly, right?
Mm-hmm.
Okay, the derivative with respect to t of the h is just going to be dH dt.
Oh my god, cannot see this color.
Sorry. Make it bigger, you can see it a little better. Okay? The green's a little tough. Alright, so that's what we've got. And there's really not much to simplify there. Okay? And the nice thing is with these, you don't really need to simplify a whole lot, because when we're actually doing a problem with this, we'll end up simply plugging stuff in for all but one of those things. Yes?
The reason why you're making it times dr dt is because you consider them to be dependent variables, right?
Yes. R is a function of time. It's dependent on time. H is dependent on time. V is dependent on time. Yeah. Okay? So now, here's an example that actually uses the work that we just did. Putting some numbers to this scenario. Let's say that we have this conical tank. The height is changing at a rate of -0.2 of a foot per minute, and the radius is changing at a rate of -0.1 of a foot per minute. Now, the one thing I want you to make sure that you do is write down exactly what you are given. Okay? Alright, so wait, it's right there. Look at what I mean. The height is changing at a rate of -0.2 foot per minute. Looking up here at the derivative, what did they actually give us? What value does that correspond to in the formula up there? Yeah, dH, height is changing, dt, okay? So we were just told dH dt is a -0.2 of a foot per minute.
So when you're saying the height is changing, so the rate of change.
Yes.
So change is r to the derivative.
Yeah, that's the dH dt. Height is changing, dH dt. All right. So then, likewise, let's get a darker green here. There we go. That'll be easier to read. It says the radius is changing at -0.1 of a foot per minute. So what did they give us there?
The radius, the dr.
dr changes to r.
That's
dr dt.
the dr dt. The rate it's a rate of change, right?
And they divide it, you know?
So that is dr dt equals a -0.1
And then they divide it.
feet per minute. Okay? So now that we've identified exactly what we have been given, we can start answering the questions. What is the rate of change in the volume? Okay, well, what exactly are they asking us to find here? What is the rate of change in the volume?
Derivative of v.
dV dt.
Yeah, it's the derivative of v, dv dt. That's what you're getting asked to find here. That's important too. It's amazing how many times students get into these problems and they have these big equations and they're doing derivatives and stuff and they don't even realize exactly what they were given or what they're trying to find. Okay, and that's where you get in trouble. Take the extra few seconds to write down this stuff. Okay? Because once you do the derivative, you're going to have something that's pretty much a mess a lot of the time. And you got to know where to plug stuff in properly. Okay? So, we've got that. We're told that r is 1, and we're told the height, h, is 2. So, let's look at this. We have dv dt, we're trying to find. dv dt, and it is pi over 3 times 2 times r. R is 1. Times dr dt. Well, that's nice. That's negative
Yeah.
1/10.
Can you like move it up because I can't see it when it's on the. Yeah.
Okay.
Thank you.
Alright? And then we have that times the height. The height, we're told, is 2. Okay?
What was 2?
Wait, isn't it r squared?
It's plus r squared, so r is 1, so that's 1 squared, times the dh dt, right?
Negative.
So negative 0.2. Okay?
Mm-hmm.
So I simplify all this, and I've got pi over 3 times, that's going to be a negative 0.4 minus a 0.2. So that's a negative 0.6 pi over 3, which is a negative 0.2 pi. Okay? So that's a negative 0.2 pi. So that is the dV dt. Now, these I do want you giving proper units of measure for. Okay? What is the unit of measure for our change in volume over time? Feet cubed. Yeah, cubic feet. Feet cubed per, what's our unit of time? Per minute. Okay? Per minute. And by the way, that's something that you guys need to make sure that you have the same units before you even start plugging stuff in. Okay? If one of these was per minute and one was per second, you would need to convert.
Okay.
Yes?
Could you please go back to the formula
Yeah, here we're losing about 6/10, a little more than 6/10 of a cubic foot per minute. That's because it's just leaking out. So the more water that's in it,
And more we-
the faster it's going to leak, right?
Right.
Because the weight of the water on top is going to push it out faster on the bottom. So as the water gets shallower, you have less weight pushing it out, it's going to drip out slower.
Is there a way
Okay?
you can find like the average of it?
You can, yeah, there are ways you could do that. That's different than some problems that you might have. You'll have a similar situation and they'll say water is being pumped out of a tank at a certain rate, at so many gallon or cubic feet per minute. That's different because in that case the dV dt we already know because we got a pump hooked up to this thing. It doesn't matter how much is in there, the pump is regulating the water flow. Okay? So there's going to be a difference whether it's leaking out just with gravity pushing it out or if we're actually pumping the water out. The pump will make sure it's constant. Here, the rate of change in our volume is going to be varying as time goes on.
So that connects back
Okay.
to the derivatives leak.
Mm-hmm.
Like it's different at every point.
Yeah, yeah.
So if the question was asking, find the average rate of change in the volume, how would you do it?
If we wanted the average rate of change of the volume, we would find the volume we started with and the volume at the end time, and we would take the difference in volume over time. Just like average velocity, you take your position at the beginning, the position at the end, and divide it by time. You get slope. Okay? That's the same thing you could do here.
So,
Okay?
so when time is 0, you have a height. When time is like 5, you have a certain.
You'd have another one, and then you would do the difference of those divided by 5, and that'll give you the average
Okay.
change in velocity.
Alright.
Okay. Or volume. Let's look at another situation here. Here we're not given a formula to start with, okay? But we have this calm, relaxing pond. All the water is still, and we drop a pebble into it. And when you drop the pebble into it, ripples come out from the center. So we have these concentric circles. They all have the same center where the pebble hit the water. And these circles are going out, okay? And if you think that's a silly example, okay, make it an earthquake. We have the epicenter of an earthquake, and we have these waves of energy rippling out from the center, okay? If you want peace or chaos, take your pick. Either way, it's the same math, all right? So here we have the situation. The radius r of the outer ripple, so the furthest reaching ripple, is increasing at a constant rate of 1 foot per second. Okay, so let's stop there for a second. The radius r is increasing at a constant rate of 1 foot per second. So what were we just told? dr dt equals 1 foot per second. Okay?
And r is equal to 4.
Well, r will be equal to 4 at the moment we care about.
Okay.
R is constantly changing, right? Because the ripple is getting further and further out.
Yep.
All right? So, it says when the radius is 4 feet, at what rate is the total area of the disturbed water changing? So here's another rate. Yeah, we're trying to find dA dt. Now, this is why this is so important to understand, because we weren't given a formula to use. But if you know what you're looking for, that'll tip you off as to what formula we need to use. What formula should we use here?
The area of the circle.
Area of a circle. We're looking at the total area, their concentric circles. So the formula I'm going to use is the area of a circle. Area equals pi r squared. Okay? So now I can take the derivative of both sides here with respect to time. Okay? So the left-hand side, when I take the derivative with respect to time,
You have dA.
I have dA dt, which is what I'm looking for. And what do I get on the right-hand side?
Pi times, can we take a pi out?
Sure, yeah, pi times.
2r dt.
There we go. We're getting the hang of this. 2r dr dt. And now, since we already identified stuff before, we know exactly where to plug stuff in, okay? So it's pi times 2 times the radius we want is 4, okay? And dr dt is 1. So we have 8 pi. Okay? What's our unit of measure? Feet squared per second. It's area, right? Square feet per second.
1 dy dr dt is equal 1 because you want.
Well, we were given that right up here. Okay? Now, one other thing I'll mention about the units of measure. Sometimes people are confused as to what to use for their units of measure. If that's you, put the units of measure in when you plug stuff in. It's 4 feet, and the dr dt was feet per second, right? Well, feet times feet are feet squared per second. Okay, so it's square feet per second.
What do you find?
So like in this case here, getting the equation was a matter of, first of all, guys, identifying what you are given and identifying what you're trying to find. And when you determine what you're trying to find and what you're given, you then start to think about, okay, is there a formula or something that relates all of these variables together? Well, with this one, it's kind of easy. We're dealing with a circle, we have a radius, we have an area. Area is pi r squared. Okay? Area is pi r squared. So that's what we're going to use is the area formula. Others won't necessarily be quite as simple. But as we look at the ones that you have to practice with here, notice the radius of a circle is increasing. Find the rates of change of the area. So this is basically identical to the ripples in the pond.
Right.
Okay? Down here, a sand and gravel plant. Sand is falling off a conveyor and onto a conical pile. All right? If we have stuff, you know, it's kind of like an hourglass, the bottom half of an hourglass. All right? You have this round base, and as sand falls down, it's going to land and it's going to naturally kind of form this cone shape. All right. So we're going to be, it says at what rate is the height of the pile changing? All right, but it's talking about, it's got a rate of 10 cubic feet per minute. So when you hear cubic feet, you automatically think volume. Okay, so how is volume, a cone, height, all of that related to each other? The volume formula, all right, that we used on that first example. Okay?
But Mr. Dixon, in the pond example, the 8 feet squared per second, that's the rate of change. Every second it increases by 8 feet?
Yeah, the area is increasing on the previous one. The 8 pi means that the area that outer circle encloses at that exact moment is increasing at 8 pi cubic feet per second.
But that's going to be different.
It's going to be different there than it was when the radius was 1 or when the radius was 2.
Right.
Okay?
That's exponential.
Because the dA dt was dependent on the radius. It had an r in it.
Is it increasing at a constant rate or no?
The radius is increasing at a constant rate, but the area is not. Okay, and that's why we needed that formula.